So, myself, I'm Bishesh. I am a director at NAAMII. The long name is there. It's a relatively long name of NAAMII, and we have a formal inauguration ceremony a while. So we would be thanking a lot of people involved at that time. But briefly, I would like to thank Khwopa College here for hosting this event. It's a fantastic place. I think everyone will enjoy this place, right? Uh, so today I would be talking a bit about machine learning, but also then introducing a bit the course structure and what we have and why we are studying this. So I think we would wait one more minute for people to settle down. Few more people have joined in. The So to the remote participants, so I'm just waiting few seconds because few more participants have joined in. Since this is the first day, so I think we all understand there are some difficulties getting everyone on time with the bus schedules and confusions. Um, so let me start. So machine learning. So what I will be doing today is mostly, there's a winter school in AI, we say artificial intelligence, but then the course itself is introduction to machine learning. So briefly go about AI, ML, and DL, what they are. I would be showing with very basics the key elements of machine learning, what there are. But whatever I will be showing in the second part, it will be covered in detail in coming courses. So this is mostly overview, right? And then again with this, how it's related to the society in general. Then we will summarize the course. So, do we have mic? So, because I would like to interact with participants. So there are volunteers, right? So let's start with some just to loosen us up. What's AI? So anyone who wants, let's try to make this interactive, right? And anyone, just raise your hand, and if you have to say what's an AI, if you have to, well, you don't need exact formal definition. You can just try to explain what it is. Anyone? Yeah. Okay. Here in the second, how many mics do we have? Do we have one, two, four? Okay. So it would be great if one of the persons who has the mics in the front, one in the back, and one in the middle at least. So this is the middle second row. Needs a mic over here. So if someone stays in the front, covering the front area, someone in the back, and one in the middle, that would be great. Thank you. Yeah,
Hello.
please say your name also, and then you can. Yeah.
Hi everyone. My name is Sandarbha Bhatta, and I'll just plagiarize your lecture from 2018 that I watched. AI is basically, first we need to define intelligence. So I think everyone knows what intelligence is. AI would just be man-made intelligence. So anything that can replace human intelligence that is man-made, mostly like computers, that would be part of AI.
Okay, thank you, Sandarbha. Okay, so he has already watched my last lecture in the first school, so there are some repetitions here, and but there's more to it anyway. Um, okay, so Zoom. So human intelligence. He talked about human intelligence, and he talked about in some sense, imitating humans. Okay, and another point of view or something to add up. Anyone else? Someone from this reason first. Okay, I will. Okay, yeah. Okay, if nobody raises hand, I will be picking up people randomly, right? Okay.
Hello everyone, my name is Nishan, and I think AI is a field which is concerned with creating truly intelligent machines so that they can be applied to a lot of other applications
Okay.
throughout the society.
Okay, so you talked about AI as a field, as an entity, or is as a. That's also fine. Yeah, so it's a field, but if you have to say, let's say a software, a computer tool, whether it's an AI or not, how would you?
I think AI is like the next big thing after software engineering. So with this we can use to solve many complex problems, just like computer vision, and learning from lots of data and making sense of data,
Mhm.
and which could be used in lots of applications, like we could even weather forecast.
Mhm.
And there are lots of application in medical field, as well as other even in education and other scientific research. So it's a really vast field, and I think we're living in kind of a new era. I think we're stepping in the new age of AI.
Mhm.
So
Okay,
that's what I
thank you.
think.
Just confirming with the remote participants, are you able to hear what the other fellow participants are saying here? Thumbs up from someone or just a chat message? Yes, okay, great, thank you. Sorry, what was your name? Can you- Nishan, yeah. Nishan talked more about the impact of AI in society. So we have AI in society and few courses or few classes within that theme, right? So um, as he expressed, so there are implications on that side also. So let's move to next slide. And so when we say artificial, the name itself, right? So it compares it comes from so natural intelligence. So it tries to compare implicitly within the name. There is already natural versus artificial. And in as Sandharva said earlier, somehow the word, the way it was described in the past, so it's related to human intelligence. Perhaps it was von Neumann who first described this term. And you might have heard about Turing tests, about how do you say, how do you say whether software is intelligent or not, right? So you could, if you have a person and you interact with that agent, let's say an entity, it could be a software, it could be a robot, it could be anything, an entity, but man-made. So artificial means it's made by humans. And then when you interact with it and long enough time, a person shouldn't be able to identify whether it's human or something else. So that's the Turing test, right? So we could go from that direction also. But just looking at human brain, right? It's an amazing piece of uh, thing that nature has given us. And if you look at not just the human brain, so if you go to the do we have a pointer? Or I can use my we cannot see the oh, we can see this. Okay, thank you, it's all right. Yeah. So some functions related with brains, right? We think of balancing. I mean, we don't think about it, but we are, I mean, somehow the functions of brains are involved in even the senses. So this could be senses, what we, the touch or the smell, taste. These things are, as you know, you might have or you have read in the high school during school days, like senses. There are five senses, and these senses come through the nerve cells into the brain. But as for us, perhaps when we look at just vision also, we see from eyes, but actually we're seeing from brain. And so as we go, so vision, even up to vision, you have animals who have this, animals can see, animal can recognize things, right? But as you go above, somehow intelligence in general, we associate language, we use it to distinguish from other animals as well, right? So it's some form of intelligence, because even defining intelligence exactly, it's a difficult job. And people have different views, but we associate certain attributes to intelligence. And we can think of these attributes like imagination, something we are able to imagine things that hasn't happened, right? And thinking or consciousness, the term itself is, people have different point of views about consciousness, but again, it's a concept or ideas associated with it, which somehow links to intelligence. So this is human intelligence. And if in the 40s 50s, lots of computer scientists and philosophers were I think lots of people thought about building machines that can think like humans, that can do things that humans can do. And this is how AI, or artificial intelligence as a term itself, was predominantly used in those decades. But as the time progressed, especially in the last couple of decades, the way the term AI or artificial intelligence is used is not exactly imitating all the human intelligence. So it's now people try to distinguish AI with artificial general intelligence, or AGI, So that's more about doing, because as a human you can do lots of things. You can talk, you can understand languages, you can see things, you can think. There's so many different things a single person can do, right? And the way the term artificial intelligence is used these days, it's like, for example, I think I have some examples here. Let's go to, yeah, this example first. So we type text in Google Translate and it translates, right? It's not perfect, but so this is, but whatever the translation tool or that software is doing, it is just able to do that. It cannot see things, but still we term this tool, that entity or that software, as an AI these days. That's how the term is used. And AGI is artificial general intelligence, and there are people who talk about super intelligence, that's going beyond human intelligence as well. But here are some examples or instances of AI where I want to emphasize it's not just about what humans can do, because if you look at the bottom left, so here it's doing two things. I think I wanted to make it a bit more interactive, but since we lost quite some time in the beginning, so I'm cutting down on some questions and interactions anyway. The two things is, one, it is identifying the vehicle, but it's doing something else that is usually difficult for humans, right? You can see that it's actually estimating the distance, and it's not obvious. I mean, for us it's difficult. If you go to the another example, where I've cropped a screenshot of from Facebook, it's suggesting things, or it's recommending things. So you watch Netflix, you use Amazon, or all these stuffs, and they are suggesting, recommending products to you from millions, perhaps at least several thousands, right, if not millions. So how do they do that? That's something humans can't do, right? So AI is not just about being able to do what humans do, but there are things and there are kinds of data. We will talk about data a lot during the throughout the school, right? So the things that humans are not able to do, but still it's some attribute. I mean, if you look at those attributes, still some sort of intelligence. And so this is. So the term AI, the way we use, it's not AGI. So I just wanted to distinguish that part. And I think I might skip this part. This is just a story in the early 60s, when people thought vision, like understanding or identifying objects, recognizing faces, it's not a difficult job. That's what many at least computer scientists thought in the beginning, and when they were giving this as a simple summer school project, or the summer project for students. And however, it's been 50 years and still an open problem. Perhaps people didn't think it was as hard, right? People talked about, okay, chess is the ultimate thing, that once humans are beaten in chess, then later people found out, okay, you can do that by brute force. And this goalpost shifting, we call it, the targets have been shifting, and now the hype is about AlphaGo, right? And it's a different way of learning in AlphaGo, if you have heard about that. But there are still so many things, a lots of, in terms of technology, in terms of what we know, what the world knows, we are still quite far away from really achieving AGI, or artificial intelligence, general intelligence. And um, we don't have a clear roadmap how exactly we can reach there. So lots of things we will learn during this school. It's not about achieving AGI, but you building useful AI tools, building or learning what are the foundations, getting the foundations for that, and also being aware or discussing about the implications on society it can have, because it's now, because it's used in so many different fields, as you will see, right? So this is how I like to describe AI, yeah, right? So this is from the first AI school slide, as Sandarbha said. So it's the ability of man-made agents that can do tasks that we traditionally attribute to intelligence, in quote. It's not that clear to define, but still of some level. So single translation and face recognition, or being able to predict certain kind of, let's say, the stock market is a very difficult job, but still people try to do that a lot, because you can earn a lot of money with that, right? So that's AI. So let's move on now to machine learning and deep learning. So what are they? Because these are the three main terms perhaps we will use. So I want to get you back to high school now, something that all of you have seen done, right? So you can think of, let's say, these data points, which could be weight of individuals, let's say here, and then the height of individuals, right? So on the x-axis, x as a data point, so it should be weight and then the height. And if we know of certain number of people, let's say here there are 10, we want to predict if new person comes in, right? So and what could be the weight of the person, that's sorry, height y, if we know the weight, can we do so? It's a very simple problem, single scalar, what we call as scalar, and something that all of us have done in schools, right? But there are even doing this, which you will perhaps get into detail in linear in regression class later today from Ayush, I think. There are already lots of elements of machine learning here. So one, we talk about data. So here we have 10 data points. Then we need to somehow get a model. We want to predict for something, for new data point. So that's the task, right? And then we need a model. So something that we have done in school is this famous equation, y equals to mx plus c. Everyone knows that, right? So what we are trying to do effectively is now we need to find a line that is best fit. So this fit, concept of fit already comes in here, right? And then there are parameters. So y equals to mx plus c, you have y and x as data points, but then you have m and c, which are, everyone knows, slope and intercept. So if we can identify the right values of m and c, then we have a right line. So that's the parameters. M and C are parameters. So we already have concepts of parameters. So if we say that regression in with ML terms now, coming to machine learning, you would say those data points as training data. All right, because you have already, so for each x value, you have the corresponding y values. And at the very basics, it's everything can be related or can be linked to this. When we now here we are talking about x as weights, but x can be images, it can be my audio, it can be speech, it can be a huge data, a video, right? It can be a graph of a molecule, or it could be a genome sequence. It could be anything. So x as an input, and we want to do some task. It could be regression. We will see some other examples, other tasks, and we need to find a model. So there is always an underlying model, right? And so the idea is which line is the best one. So we need to somehow fit, and there comes the optimization problem. And what we call as learning is, in the end, we are trying to optimize these parameters. So here the parameters is m and c. So we want to optimize that, and which one is the best. And then to optimize, you need to somehow know, you need to have the sense of which one is better. So comparing models, somehow you need to compare things. There comes the idea of distance. Or if you go into math, when you, perhaps people will talk about metric, right? So it's effectively, you can, loosely speaking, we can say as a distance from the, we want to get the target value, and are we there or not. So we need to optimize that. So this is the idea. And then people talk about, oh, we got measurements, but there are errors in measurement. There will be uncertainties in measurement. We are measuring, there could be human error, there could be error from device. So when you get these signals like x, it can be noisy. It might not be exactly what we want, or even in the model there can be errors. So these errors, again, this will be talked in detail in coming several lectures. Here I'm just trying to give the broader picture, right? Why we need things, or those lectures. So then so here it's not exact straight line, because we don't need to be. So if you go here, earlier I had straight line model, but maybe it's not a straight line, the exact underlying model. So it could be something else. So we can think of a general function, a polynomial function, or something else, right? Still a regression. It's not linear regression, but still a regression. And then we have this error term, epsilon, and we can think of this error term in many different ways. One is probabilistic point of view, which you will learn. So that's why we need probability and statistics. You can put some distributions. Again, going back to school, everyone has learned Gaussian, right? So if you think of this data point or this model which has certain uncertainty, and if you have a prior of saying Gaussian, then these equations will turn into least squares. So you can think of this as optimization problem. I'm giving keywords just to relate, because these we will go into detail later on. Like you might have heard about Lagrange multiplier when you talked about optimization, and you can think of optimization problem here and the regularization term. But you can also think of this as a maximum likelihood estimation, where if you have Gaussian, then when you do the maximum likelihood estimation, you will end up with the same. Here it will be prior on this noise. So this kind of, okay, so from the simple data points, I'm already talking the language of prior or posterior or maximum likelihood estimation. So all those things you have learned in school again, and these are the foundations. And your Bayes rule, with the famous Bayes rule, you need this. You need to be able to, when you, and it's not just about weight and height. So we could think of what I'm speaking, and we want to transcribe what I'm speaking automatic, like what Zoom does, right? So there are underlying models that you will perhaps see in speech courses, which boils down into building probability distributions. You have a vocabulary of all the words one can speak and the frequencies, and you build probabilities, and you have priors, and you want to estimate the posterior, or you want to estimate the likelihood, and it all boils down to it. So you need to be able to distill down, or you need to be able to pose your problems, real world problems, into the language of equations, language of maths. And that's why you need these foundations. I mean, if you think of machine learning now, again, the data can be different. So the real world is not always easy, right? As life. So you can have uh, different types of models, which we don't know exactly which models, and we need to learn these models. So we could have some priors that you can use. Okay, I want to go linear, or here it could be some sinusoid kind of waves. But then when the new data comes, the story might be different. And so if you think of machine learning as a black box, that box can be fairly complex, as like deep neural networks we will see. You will see many different ways of building this function, where you have the input and a theta. What you are trying to do, this theta is not just a scalar, so it can be 1,000,000 dimensional data point. And we will see one example of how to think of this data as a point in a Euclidean space. So we'll briefly go that, and we then later in the linear algebra course, perhaps we'll go into depth why we need linear algebra and all those stuffs. But here, and then we want to predict the output. So learning, whatever we call as learning in machine learning, in the end turns down to be, so you have a data set, so set of training data, certain numbers, and you want to find best theta parameter. You need to optimize it, and to optimize, you usually have a distance, where for the observed data points yi, you want this function to get as close as to this. So you want to minimize the distance. So if you go to the very complex machine learning systems, in the end, well, there are supervised. Let's say this here again, you will distinguish between supervised, unsupervised, and other tasks. But in general, for the supervised tasks, you can propose the problem in this setup, all machine learning problems. And what will change is the data, the models, the way you optimize, and the way you pose distance functions. So in the end, all your, even like any real world problem you do, you are able to pose into these sums. In most cases, there are some exceptions, like when you go to reinforcement learning or some other things, there will be different ways. So I want to pause for a few seconds, but here let's have some interaction, right? So think about what could be data points. I already said some of those, but still I think it would be interesting to again listen from some of you. Anyone? So like these, any of these questions, try just, let's brainstorm, or let's, who wants to first speak? Okay, second here. What's your name? Yeah, I'm picking up people also. So yeah, yeah. Yeah. Please say your name and then. Yeah. What's your name first?
My name is Durga Pukrel.
Okay. So any of these questions, what do you think could be others? So I gave an example of weight and height and the data points. So in machine learning, real problems, not just that regression, but in real machine learning problems, what could be like data points X? Any examples?
In my point of view, X could be independent variable.
Okay, so that's a definition kind. Yes, it's in, but real examples like any real examples of machine learning problem that you have seen people doing or you yourself have done where the input X data, what kind of data it could be?
Mm, while fitting linear
Yeah,
regression.
but no, not just linear regression. So we are going beyond linear regression now. So
Yes.
what we are saying now is the machine learning where you have the input data and you have a model. This model doesn't need to be linear regression. It can be anything. It could be deep neural network. It could be convolutional neural network. It could be graph neural network. It could be so any general function that you want to do where you have certain parameters, right? And you're predicting something. Let's say there's prediction, inference, there are differences. We'll talk about that perhaps in detail in later courses, but let's say here now we are just, you want to, it could be classifying. So I will go in the next slides, I will show there's something else than regression as well that we can do, but there are many other things we can do. But think of this as it will create some output, the optimal output that we need for the data. So so the example I showed earlier, the translation in the Google. So can you think of what we could have here? What could be X in that example if we are doing translation?
Sorry, I
No?
have
Oh,
no idea.
okay. So anyone else? Anyone else? Okay, here. Say, second row, please.
Hello everyone, my name is Rasmi Bhatrai, and here I want to answer the last question, what distance to minimize. In my opinion, our main target is to minimize the distance or the difference between the real value and the value that our model predicted.
Hmm.
Yeah, I think that is my opinion.
Okay, thank you. So distance. So again, when we let's say, I think I didn't have again because I didn't want to repeat a lot from my previous slides, but even in the distance, so it's not as trivial, right? So if you think of weight as a single point and you want to find the difference between two weights, so let's say someone is predicting my weight and it says, let's say, I don't know, certain x1 kilos, and then actually my weight is x2 kilos, then how do you find the distance? There it might be easy because you can just say subtract that. But think of image as, so when I said to Durga that what could be x in the Google translation, so if you think of, so this place here, the X input is the sentences that we input. So a sentence, an English, let's say English language sentence, this is a winter school, if I say, that's already an X. So this is what I want to encourage you or try to um, uh, explain to you. One key takeaway from today's is that think of this x or y not just as scalars, as single point value. It could be any big, it could be a big image, it could be the whole video recording that we're having here. Let's say we have some colleagues or friends here who are doing summarizing videos, let's say from this whole video, let's 1 hour lecture video, you want to have an AI system that automatically summarizes it in 3 minutes. So for there, that whole video is X, single input, and you want to have a model, that AI, whatever we are saying, is a model with some parameters. It could have millions or billions of parameters. That's okay, but still a model that will give an output which is the 3 minute thing. That's Y, right? And then we want that Y to be as close to the reality as possible. So there, how do you define a distance between, let's say, let that model, this F model is summarizing our video into something that is talking about Dasai, let's say. Instead of talking about machine learning, the output from that video summarization, the audio, it talked about Dasai, let's say, right? But I'm talking about machine learning. So how do you, or even in machine learning, let's say it's talking about deep learning explicitly as an output, the model output. But then if my whole video was about basics of machine learning and linear regression, but how do you identify the distance between a text or a body of text, that's or a paragraph, and another paragraph? It's not obvious, right? So thinking about distances, that's where all these transforming data or getting data into first into right format, and then finding distances. So you have talked about mostly you've learned about Euclidean distances. So x1 side, yeah, if you look at my first AI schools video, I think it's there also. So if you think of x1 or x2, so x1 minus, I think many of you memorized x1 minus x2 whole square plus x2 y1 minus y2 whole square as a distance between 2 points, right? So there you are talking about x-axis, y-axis, and you're plotting a point. We don't have board, right? I think maybe from we for now it's okay. I think it would be nice if we have a one board where we can write. For later, that's fine, okay, because it's easier to show. But these distances for images, so if I capture one photo here and I capture another photo here and I want to compute the distance between images, again there are difficulties. And if you think of Earth, so I'll give you very simple example, okay, that's I think. So if we want to compute the distance between here to New York, how do you compute? So do you go a straight, if you draw a straight line from here to New York, that straight line will pass from inside the Earth, right? So you need something else. So you heard about perhaps the geodesic distances or manifolds, all these different things that you might have heard or you might not heard. But what I'm trying to say is there are complexities even defining distances, and it's not always obvious. And this is where you need all these things about vector space, linear algebra, and then going into other kind of distances. You need to understand this, and because in your real world problems, trying to find the right distance, because your distance is very important, right? Because you are trying to optimize that. So or later we will see it as loss functions in the deep learning terminologies. So there is lots of space there to explore as well. So those kind of things you will be learning. Then in terms of tasks beyond regression, anyone? Yeah. Okay.
Hello everyone, my name is Anita Baral. Tax beyond regression, linear regression, as we talked about, then there is logistic regression, there comes. Then along with that, there are neural networks, different types of like prediction algorithms are there, and as well as computer vision problems, natural language processing problems, as well as like general adversarial network problems
Okay.
as well over there.
So those are architectures reflect in terms of tasks. If you think of tasks, so regression, the another example could be classification.
Yeah,
So this is
yeah.
what I was trying to go into, is like you are regressing a point or something, interpolating a value, then but then there could be categories. So you have input. So here, see, now X is a whole image. It's not just a single point, and you could have cats or dogs, and you want to classify for a new image that comes in whether it's cat or dog, right? So this is another kind of tasks. So uh, we will be covering lots of different kinds of tasks as well, right? And in this school. Now again, there will be complexities. It's not as easy as, okay, you have a model, you get bunch of data, you collect thousands of data, and then you train a established model. You will get some accuracy, 60%, 70%, and 90%. But the real world is different, because sometimes you can get this. What is this? Anyone? You don't need mic. I think you can just say cat. Okay, yeah, cat, or maybe it's dog. So there can be difficulty. So this is, so here you will talk about decision boundaries, right? So the decision boundaries. So here I'm just showing you on a linear space as these, but in reality these images don't live in this space. So for many of you, I think this is where I think it gets slightly difficult to grasp the ideas. But this is important, and I suggest or I advise you to try to think of data and the space. Where does it live? Because most of the undergraduate courses here in Nepal, you don't hear about manifold or all these kind of things, right? And this distance, metrics, manifold, these kind of things are important and quite useful, and hope you will learn some of those during this school as well. But here we're projecting into 2D space, and it looks, sometimes it looks easy, but then it's not always easy. So, and then how to find right decision boundaries, or how to project these data into right space where these are nicely clustered, nicely separated, and these kind of things. Again, there's lots of interesting ideas people are exploring, and some of them will go. Yes, please. Regression, yeah, regression, yeah. So in regression, the task in the, I mean, the earlier one, we are regressing a point, a continuous point, because it could be in any range. So let's say in a real line. So you could be 1.5, 2.5, or 25, 30. So that's regression problem. So you're trying to regress a value. While in the classification, you have a fixed number of categories. So you are saying either cat, dog, or if you think of so it's a discrete set of so it's finite set of categories. Yeah. Uh-huh. Yeah, 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 yeah. You can, yeah, yeah. So if you go into prediction and inference, yeah, so there you are predicting something, but we could also infer the parameters and do something else also. Yeah, yeah. So there's different ways of categorizing. So this will cover. So again, I'm just giving glimpses of different things in this course right now, but those details, different kind of tasks, you will get to know more as we go into different courses. Yeah. So this is again, we are optimizing finding a best theta that can say classify whether the image is dog or cat, and it could be anything else, right, depending on the problem. So AI, we talked about it in a very general sense. We try to define it in some sense, right? And there are many ways of doing AIs, and traditionally people have done in many different ways. But this school, although we will mostly focus on machine learning, which is what we showed earlier as a framework where we have a data, as we saw, a set of data. It could be labeled, unlabeled, that comes later, like supervised, unsupervised, you might have heard. But from those data, we want to do some task, but we don't prescribe exactly what you should be doing. It's not like an algorithm where we say you write a line of code where you do this, that, do that, and then you get this result. You don't do that. You have a model with parameters, and you try to optimize it or learn in a different way. So you want to learn, so learning underlying, there's optimization. That's why you will be also needing calculus and all those background, which will be covered, I think, in second day, right? And so that's machine learning. But so that we will, even within machine learning, there are many different ways of doing machine learning, but predominantly of late, mostly for most cases, it's not 100%, there are still other methods, but deep learning is used. So now we will try to go into deep learning, right? So how much time we have? 30 minutes, okay. So first, even going before deep, neural networks. So what's deep neural networks? Okay, let's hear from folks in the last rows. Anyone? What's deep neural networks for? Okay, yeah, thank you. Please use your mic, and please let us know your name first, and then.
Hello?
No, mic is not working. Another mic, please.
Hello? Hello?
Yeah.
My name is Arpan Gemali, and deep neural network means having more hidden layers.
But what's neural layers?
Neural network, neurons.
Yeah.
Neurons are just every neurons can be used as a parameters.
Okay.
Parameters to determine something,
Uh-huh.
and and the neurons in the hidden parameters are more.
Okay, I think that's also fine. So I just wanted to, because a lot of people, not lot, but I have seen people getting confused with deep neural networks. So it's like brain networks, saying. So that's, I just wanted to clarify. That's why I asked the question. That it's not really we don't really know how exactly brain functions. I mean, there are things we know, but there's a lot of things we don't know about human brain. So it's loosely inspired from neurons. So you might have seen in schools this anatomy, neurons cell. You have a long axon and then dendrites. So signals goes from axon to dendrite, and it passes on from synapses to another neuron and another neuron. So it's loosely inspired from that, but it's not really. Deep neural network isn't really emulating brain. So I just wanted to clarify. That's why I asked this question, right? So it's, and as he said, we have again. So we go back to linear function. So I showed you linear regression earlier. So it's exactly the same thing here. The only difference is there we had a scalar value as x as a single weight, and here you have a vector. So x1, x2, x3 that as an x. So x itself is with 3 components, so it's a vector. So as I said, x is very generic. The input data as a vector, it could be a complex structure, an array of, so it could be anything, right? So here it's a vector x, and it's still linear regression, because what you are doing here is y equals to mx plus c goes into z now, the output, and m slope now becomes not a single parameter but 3 parameters, weights. So now I'm slowly moving into another notation, so because you will be hearing a lot about weights in coming lectures, right? And you have this, so you are multiplying these weights to the input data, and you are adding us like a bias term here. That's why b, it's okay, yeah. Does it work? Okay, but okay. Uh, I think that's fine. Thank you. Because yeah. Okay, thank you. I'll show with the cursor. So now it's just look at this in a different way. You can think of this as a single neuron, or neuron in deep neural network sense, not necessarily the real nervous system neuron. But loosely inspired from that, or perceptron. So you have input data, you want to learn these weights, just like the m and c we wanted to find. Here we want to find w's, right? And the terms now goes into input layer. So now you have this as an input layer, you have an output layer which is z, and you are trying to learn. So this is again linear function as a neuron. So this is, but what happens, I think you already saw earlier as well, is real world is not always linear, mostly non-linear. So if you have a non-linear in reality a function that we are trying to estimate, or a model we are trying to get close to, if it's not linear, like you saw earlier with the sinusoid waves or parabolic waves, or it could be even classifying the images into cat or dog, they are not linear. And this linearity, non-linearity, and these sorts of things you will be, I think, learn more in linear algebra and in optimization courses also. So we cannot really use linear functions to estimate or model non-linear stuffs. So what do we do? Or it has limited representation capacity. That's what we say. These W's can represent very limited amount of information, but we can compose multiple layers. So here it's still the same thing, but you are composing the layers here, 2 layers. So now the hidden layer, what he mentioned about this ideas of hidden layer comes, and even with composing, you are still not good enough if you are only linear, and that's where the non-linearity comes in. So what you have heard about activation functions, so this will, you will go into real detail, I think, in the second day perhaps, when you talk about neural networks, right, and how to train those. But here I wanted to use the same model or same approach as what we saw in the machine learning. You have input, you have model, and you are trying to give an output. It's similar, but here you are organizing these nodes in certain way. You have hidden layers, and you have non-linearity. And if you compose now this to many layers, you get deep and deep, and that's how you get into deep neural networks. So from a single neural network, a small one model, to a deep neural network. And deep neural network is, again, if you go back to that model f of x theta, so theta are now these w's, right? and many W's. So if you have here green, this one set of W's, another set of W, you can go really deep, or you can organize this in many different ways. So you will talk about CNNs, GNNs, and all these architectures. They're nothing. They're just different ways of organizing or different ways of connecting these parameters weights depending on what problem you are solving. If you are solving images, there because and images have certain structure in data, right? So you have, if you think of if we take a picture here, the neighboring pixels have certain relations with the nearby pixels, and it's continuous in some sense, or there's some certain organization of the way the pixels are organized in certain ways. If you think of language, the sequence of words have certain way they are organized, right? And so these priors are what we call as inductive biases. We try to enforce that into this general setup. So with this one, with the nonlinear function, it can estimate pretty much any function. So there's this universal approximation function. You'll get into the details, I think, when you talk about graph neural networks. So people will show some of those. But then we want to enforce some prior, because we know we have more knowledge about world, and how do we impose those knowledge of your world of or the problem you are solving into the system. So that's what you will see in CNN lectures. When you talk about convolutional neural network, you'll be hearing about parameter sharing. You'll hear about these shift invariance, shift equivariance. So I'm just giving these terms. No need to understand every term. It's just to give you the like a trailer of what comes in the coming days, right? And but why do we do that? Why do we choose CNNs over something else? These days transformers are getting quite popular, or LSTMs. You have heard all those things. So depending on problems, depending on the tasks, depending on the data, which one could be useful? Why should we use those, right? So those kind of understandings is something we I hope you will be able to get in the that architecture day, where you have many different architectures for neural networks. So so that's deep neural network, and deep learning is learning on this special this kind of specific architecture. So it's a subset of machine learning, as we saw earlier here. So from AI to ML to we now come to deep learning. For example, in graph neural networks, actually it's not really deep. So you'll also see those things. So it's sometimes it can be confusing, but they are shallow networks. Deep networks doesn't always work, at least in graph neural networks, and you will learn in why, or at least actually I think it's still an open problem to know exactly why, but there are certain theories, and people are beginning to understand why it doesn't work there. And you will actually get to listen from people who are working on that and have published the most recent results on those topics on graph neural networks also, when you that we have one whole day for geometric deep learning, right? So now let's get back to this again question about data, real world object as data points, because that's in the end this is what you need, right? So you have a real world problem, and you want to solve it with machine well, if machine learning is useful, you want to solve with that. So the first step is to how do we pose that problem and get data. What would be the data in that structure we saw earlier, in the framework we saw earlier, where you feed in as the data, and you have a model, and you get the output. So what's the task, what's the data? So here is, I'll give you an example from image, and over the course you will see many different examples in applications, right? So when we think of computer vision or images, many of us, we just take it granted, right? We can see things, we can walk. I came to Khwopa, and when I go, even if I come once, even if to the new building where I haven't been, I can already imagine. If I see from outside, I can imagine how things are. So we make the map of the world. So this is a 3D world, and we make the whole map. But if you think of cameras, or the making robots be able to navigate, or making computers understand, give them this vision. But what we see here is you already, within a fraction of a second, you already infer things. Okay, this well, there might be some confusion regarding whether it's a leopard or a cat, but still you have the beach, you have sky, you have leopard, right? And for us it comes so naturally. We don't even think about this as a very hard problem, perhaps many of us, right? But this is a very difficult problem for computers. And for computers, when the camera captures this, it just sees numbers, and these numbers can change very wildly when you take the same picture but in a different setting, like when it's cloudy, if it's rainy, if it's in the evening, right? Things change a lot. If it's noisy, or even the different cameras, there's so many variances of variables that changes this number so drastically that it's very hard to build a logic or build a logical algorithm to be able to let computers say, okay, if you have, let's say, this number of blue pixels, if this number of white pixels, or blah blah blah, these numbers, you say this is a cat. It's very, people were trying to extract features. So that's again in computer vision, or perhaps when you I don't know if we have computer vision dedicated lecture this year or not, but first winter school, if you look at the videos we have in length going into in the YouTube, by the way, if people don't know, you can find all the first winter schools videos on YouTube, and hopefully very soon the second one also, and this one, all the lectures will also be published in YouTube after the school. So the challenging problem, but for us right now, I'm not going into the difficulties and what people, how machine learning and traditional vision problems are done, so I'm not going into that detail, but I would just wanted to abstract this into how do we get that as a data point. So we talked about image, but we want this as a data point, right? So these numbers, you can think of this as a function where you have a multiple so 2D, if you think of 2D image, let's forget about 3D for now, but if it's x and y, so you have a certain x and y position where you are putting some value, right? So for any given xy position, you have a value, and the value has a certain range, usually from 0 to 255 or 0 to 1, depending on how you describe the form, what format you use for the image. And so you can think of this as a matrix. So if it's a color RGB image, you will have 3 channels, and then you still have a matrix. So, and from matrix, you can actually think of this as a point as well if you vectorize. So this is a vec operation. So what you are doing, so let's think of this 2 by 3 image, a very small tiny image. You have just 6 pixels, and in the 6 pixels you are vectorizing. So first row as the first 3 point column components, and this last 3 components. So if you do that, so this you already know from high school maths, right? You can so any vector is a point in this for you. If you, I think you maybe you just saw 2-dimensional and 3-dimensional vectors, right? So you have 2 xy or xyz, and that you plot as a point in a space. So when you, but it's the same thing here. This, the dimension number is increased. It's a 6-dimensional space, and you can plot this as a point on a 6-dimensional space. As that image becomes now a point, data point. But that's where, so I don't have those detailed slides here, but where you can see these points, if you compute distance like x1 minus x2 whole square plus y1 y2 z1 or x1, so there are 6 these things, you don't get these distance between images is something more. When we think of distance between images, we talk about semantics. So if I take a picture here, I take another picture here, we talk about similarities, whether there are people or not, whether it's both are cloudy days or not, or there's so many different things, and these are all features or ideas or concepts that we have already in our mind. So our brain is already actually processing. There's lots of processing already involved from images, where it builds a representation of those images into something else from the raw images. Those are not those numbers or vector points, and that's where this whole representation learning thing comes in, where you have the input data, you can put it as numbers or vectors or arrays. So that's something you do as the input to the machine learning model. And now the machine learning model, especially deep neural networks, what it is doing is it transforming this data point into some other forms. It's projecting this into some other space where you are learning certain kind of features or representations. So you'll hear these terms, or you will get into detail into this, where it makes it easier to do whatever task it is doing. So for example, if you are classifying the images, so it want to project all these images into a space where all cat images will try to group together on that space, right? And that space is, I mean, it's a bit abstract for you now, but hopefully from linear algebra, and when you get into more detail, you will understand a bit more. So all dog images into another group of space. If you can group, if you are doing classifying, if you are doing classification problem, so if you are classifying cats, dogs, and let's say humans, now I give into 3 classes, then you want to project this data point, so you can have every image as a vector. Here you have, I don't know if do I have, okay, I don't, so you can think of, okay, let me ask, I think it's easier. So this is a 2 by 3 image, that's why you have this dimension, 6 dimension. If we have 200 by, or let's say 500 by 500 image, usually that's the sizes you get 240, 500 resolution, right? Or even beyond if you go to SDs. So what would be the size dimension of this vector if you do vector of anyone? 500 by 500. Yeah, yeah, so that's how much? Yeah, okay, 5 lakh. And if you go to 1000 by 1000 image, you go 10 to the power 6. So see how the dimension is increasing. So when people talk about million dimension, it's not, I mean, it's just this. So, and that's not just image. If you think of let's say the Facebook profile, you can have so many categories or kinds of data and the dimensions. So each of these categories are kind of let's say the profile name. You can have age, you can have height, or all these whatever information you have, right? So all these goes into one attribute, and these attributes becomes one component, and you can build out this huge dimension data. So the image, it easily scales up into 10 million 10 billion dimension, right? And but that's too big a number. When we talk about even this image here, it, I don't know how big is this, but you can think of this as, let's say, 500 by 500 or 1000 by 1000, so 10 to the power 6. So you have 10 to the power 6 numbers. But when we think of image, we don't think of so many 10 to the power 6 numbers. We think of there's a cat, there's sky. So we are encoding the information, or we are abstracting this information into so few number of things. So there must be a way to represent these big, huge dimensional number as data point into a small set of things, small set of numbers, which will be close to the way we see, like with the way we say a cat, or this is the sky, or whatever problem we are doing, as I said earlier, in a small. So we could boil down all this data into, let's say, 5 dimensions, 10 to the power 6 dimension input data into 5 or 6 numbers. And this is representation learning, and this is what most of deep learning is doing at the end. You are transforming the data at every, you saw that layers and layers. So at every layer it's transforming this data and building representations out of it. And there too, so there are some motivations about human brain, the way human brain sees and it processes. So it's at different levels of vision. And again, in the computer vision courses, if you check in our previous winter schools, there is we show some examples and analogies of how human vision, it's still, again, as I say, it's not everything is understood, but there are research works which shows we know certain things about how images are transformed and how different features of image are computed in the brain, and convolutional neural networks, and these are also loosely inspired from those observations, those learnings, right? So that's representation learning, data transformation, data point, mostly deep learning of different ways of doing things. That's what you will learn. But it's not just image, right? So we will go into language, it's the same thing. So you have language, you have words, you convert them into tokens, you get a vocabulary, a big matrix for vocabulary, and then you try to encode them with positions or numbers. So you get a number, a big matrix, or a vector. So that's what you will do. And then you will try to build a machine learning model which will transform this data into a something suitable for your task. But then it will, this transforming the data will be done by those parameters. So you have theta, which multiplies the input, right? So it's the same thing. So with different architectures, in the end what they are doing is you are multiplying these weights to the input data, you get a new intermediate result, which is a hidden layer we saw earlier, and from that hidden layer you again transform with another weights, another weights, another weights. So it keeps on transforming these data. But while doing this, you need to find right parameters, and that's what learning is. So you have a loss function where you try to train the data with the observed data in supervised setting. In unsupervised settings, you do something else, which you will learn later. But in the end, you are trying to find these right parameters which will transform this data into right representation that will enable you to do the task you are doing. So I'm saying, if you carefully listen to my words, I'm putting this in a very generic sense. So sometimes it can be difficult for you to exactly see what I'm saying, but over the course you will see these instances, and when you recap, I think you will understand. Oh, okay, yeah. So I'm synthesizing these different ways you will do this machine learning, right? So again, points. So you think of data as numbers. In the end, you will get this in matrix or arrays or sets. So you will get into a certain form. Then you have a certain task, and you need to identify right task. You need to pose that problem into right task. You will have model. So from linear regression to a fairly complex deep neural networks, in the end it's just a model with parameters. So which one to use will depend on the problem. That's what we talked about, inductive bias or different kind of models, architectures, right? And what to optimize the distance. So I gave you a few glimpses of or examples of how distances can be not trivial to define, and you will learn more on those things. And then this whole optimization. So if you set everything rightly, you still need to do the optimization, and you have, and that's again not always easy. So there are lots of different ways of doing optimize. To get to a certain point, it's quite easy as well. So if you, even the high school students with good programming experience, certain programming experience, can build a basic machine learning model, right, in a day. but but then it will have certain accuracy, but it won't work for new real world data, and that's where the challenges are. So the whole goal of this school is to not just, for you to not just be able to, okay, we have this data, I put that as a data framework, and here is the model, okay, I will you choose from this model, and then I get the result, okay, I got 80%. Now I have a new data, oh my, now accuracy drops to 40%. Now what do? I don't know. So that's my observation. For most people who come to us at NAAMII as well, have done lots of projects, there's lots of machine learning courses, but the point most of them reach is knowing these different architectures and being able to train a certain model and getting certain accuracy, but when the accuracy drops in the real world problem, because that's the reality, don't know what to do. So hopefully the course will help you to think beyond that, or go beyond that level where almost everyone can train machine learning model these days, right? And but so that's something you will learn beyond those points. So those points are the basics that you will always see in every machine learning or different approaches that you will see. So I'll go slightly. So we have 4 minutes left. Perhaps we might go 5-10 minutes extra because we lost some time earlier. So this is for people who want to build products or who are building products. Um, we could go one whole lecture on this actually, but for today we'll just briefly brainstorm or talk about this so that you start thinking about that, right? If you look at traditional software products, let's say Zoom as a software without machine learning model, it just needs to function. So you specify for a general software, or let's say Excel, right, or even simpler, logging into Gmail, let's say these softwares, you have certain specifications, you specify functions, and the software will do that. The software does that no matter what. There is no 60% 70% thing. Logging in, you have to log in, that's it, right? So obviously there are other things like optimizing speed, security, those things, and there are lots of things people will try to work out on the software development side, or even building right way the software, generality, modularity, all those things are there. I'm not ruling out that, but as a user, as a product that you serve the user, there are specifications and you meet it. There is no in between 1 and 0 for most things, most of the software. But machine learning is something else. This key difference is, you might have seen Facebook's face tagging, automatic tagging, right? So it's been there for years, and you all are used to with it not doing right several times. Like, okay, it tags someone else as you. So, but still it's deployed in as an industry, it's still deployed, and customers or consumers are using it. So this is, I mean, it looks obvious to you, but it's a very important difference. because then it comes down to, okay, how many times can Facebook afford to do mistakes on that tagging? Or how do we define what is the right amount accuracy? And accuracy can be, or let's think of chatbots. So you might have used chatbots in different instances. It works, it doesn't work, but industries are still deploying it, right? And when is the right time to do that? What are the metrics? How do we measure this? So there are lots of these nuances involved in machine learning models, and there are, so function and performance sometimes can be blurrier boundary. So that's what I try to say. So even specifying the product. So okay, if someone says I want a chatbot and I want, okay, these many questions to be answered, but then these many questions can be questioned in many different ways, and it's not possible, at least until now, from the given nowhere in the world can any chatbot answer everything. Like you cannot be like a human, right? But so where do we, how do we define those metrics, specify this as a product, right? And finding the right metric is not obvious. That's what I'm saying. And then the biggest challenge in machine learning right now, it's an open problem, is you train in a certain kind of data, right? Let's say video summarization, if that could be one example. So certain kind of data, certain kind of videos. If you're looking at just the audio, it could be on the background or in certain language, and then you go to some another language, some other settings. The same model that you trained, which is already trained, and now you want to use it for new data. If this new test data is different, so we talk about domain shift, population shift, the different ways people talk about shift of data. The result can go down really badly, and this is generalization problem, which is quite challenging. And another aspect, as a product designer, people who are doing products in ML, I think, will have to think somehow of human in the loop, because there are many instances where the machine learning model or the AI will not completely replace human. It will be automating several tasks, but there will be instances where how do we engage human and the AI in an optimal way? So even from the design process thing, when you design these systems or tools, if you think of this human in the loop, it can be useful way of thinking of, because it may be the task you are trying to solve will be simpler than what you initially thought it would be. What is the real need in terms of the problem? So these are, I mean, we could go in the whole lecture, I said, as with examples, but for today I think we will leave that over there. And the data type and applications comes out from data types. Like we can work with images, videos. People talk about computer vision, but those images could be from medical images. Then we have biomedical imaging applications. We talk about speech, natural language processing. So these are just X, nothing else. So don't get um, scared by these complex data sets. They are just X in the end. Once you know how to get to that X and fit into the model, things become simpler, right? And genomics data, biomedical images, even financial data. So these are the things that we will cover in the school. So I just put those, but there are obviously more kinds of data, right? And we will cover more as well, I think, in certain molecular data and those things as well. Now comes the, so when we already see here data and we think of finance, insurance, health, genomics, videos, images, and the way that we live in the virtual world these days, and the way we have machine learning or AI in everything. So there's something else in this course also which we will discuss. And again, here it's not solved problems. It's not like we will be prescribing you do this or do that. It's more about opening up this area and letting you think, or helping you think what are the implications in the society. When we build tools, let's say, I mean, you might have heard about Facebook, is it that they're not using face recognition anymore, right? So these kind of issues are ethical issues, or how are we impacting the society with these tools, because it's so pervasive now in so many different fields. When we build tools, at least thinking about those, so it is ethical. Like at NAAMII, we're doing one project where we try to so this is with another research partner, where we want to see the prevalence of intimate partner violence. So it's a violence between, now in the digital age, lots of partners, they interact online, and in the online there can be violent behavior, harassment with and in people can do in Nepali writing, like publishing some personal photos on the website and then saying really bad things. And if you want to control that, you want to be able to detect it. And to detect it, you need data. And getting data, or so there comes this issues of privacy and how to do it. I mean, our end goal is quite, I mean, good. You want to prevent this, but then the process itself has so many challenges and ethical dilemmas. How do we deal with those? And we don't have answers to everything, because it's relative everywhere. I mean, in the world, people are still trying to work out these things. Or think of face recognition, or the drones applications where we goes to the military. What happens when military uses is to kill millions of people? So we all these, cliche like sounding things about, oh, technology can be used for bad or good, but you might be working on those technologies or the topics which will could be used for something really bad or for something really good. It's not that everything is bad. There's really good things also happening, right? So many opportunities. But so at least thinking about those things. So that's some of the courses will talk about privacies, this because the data is involved. Some things will talk about implications and all those stuffs as well. And also there's some, even from the business point of view, we talk about winner takes all dynamics. This means it's as you, if the companies get bigger, bigger companies have lot of advantage because you have more data, you have more manpower, and it's can be difficult for smaller companies. And so these are this kind of AI system has I mean certain socio-economic implications. So it's also to encourage people to think about those stuff, right? This, I think I'll skip this. It's just to say how different countries are building strategy, and it's even old slide where I think 2018, until 2018 there's so many countries already building national strategies for AI. So just showing that there's how it's the implications, what kind of implications it's having in the society, right? So governments are acknowledging that just for that. And I'm trying to, I think so we have last few minutes, I'm already 5 minutes beyond. So we have foundation courses like linear algebra, probability statistics, and found machine learning, and I try to put AI society, AI ethics also as some sort of I mean still foundation, in the sense that we need to at least be able to think about those or know what they are. We have applications, you might have seen computer vision, NLPs, and okay, instead of going into every, I'll just put this slide, and perhaps you all have these too. Oh yeah, this is also, I hope people will enjoy hiking, so we have that. I will, yeah, keep this, and let's have some questions now, I think. Thank you. Yeah.